Good morning, students. Myself Vaidegi, working as assistant professor in Sri Muthukumaran Institute of Technology. Today the video lecture is from the subject CEC Analog IC CEC 334 Analog IC Design. In this video lecture we see the topics from the Unit 5 of Analog IC Design. Today we will study three important structured design for testability techniques: level sensitive scan design, partial scan design, and built-in self-test. These techniques are widely used in modern VLSI circuits to improve testing efficiency and fault detection. They help engineers verify complex integrated circuits quickly and accurately. First, we see about the introduction to structured DFT. As VLSI circuits become increasingly complex, testing becomes a major challenge. Internal nodes are difficult to access and faults may remain hidden. Structured design for testability introduces special hardware and methodologies that improve controllability and observability. Three commonly used techniques are LSSD, partial scan, and BIST. Next we see about the scan design concept. The scan design concept forms the foundation of many testing techniques. In normal operation, a circuit behaves as a sequential design. During testing, scan chains allows us to treat the circuit as a combinational system. Test patterns are shifted into the scan chain, responses are captured, and results are shifted out for analysis. This greatly simplifies testing and improves fault detection. Next, we see about the level sensitive scan design. LSSD was first developed by IBM as a reliable scan testing methodology. It uses level sensitive latches instead of conventional flip-flops. Conventional flip-flops separate scan clocks and system clocks ensure predictable operation. One major advantage of LSD is that it eliminates race conditions and timing hazards, making testing and independent of circuit delays. Next we see about the working of LSSD. Operation of LSSD follows four basic steps. First, test data is shifted into the scan chain. Next, a system clock pulse is applied to capture the circuit response. Then, the response is stored in the latches. Finally, the captured response is shifted out and analyzed. This process provides excellent visibility of internal circuit states. Next, we see about the partial scan design. Full scan testing may require significant hardware overhead because every flip-flop is converted into a scan cell. Partial scan overcomes this limitation by selecting only important flip-flops for scanning. These flip-flops are usually chosen based on testability analysis. Partial scan reduces area overhead, power consumption, and performance degradation while still providing good fault coverage. Next we see about the comparison of full scan and partial scan. Full scan offers very high fault coverage because all flip-flops are accessible. However, it increases chip area and may affect performance. Partial scan reduces hardware requirements and power consumption but may provide slightly lower fault coverage. Designers choose between the two methods based on application requirements and cost constraints. Next we see about the built-in self-test. Built-in self-test is a technique where the circuit contains its own testing hardware. Instead of relying entirely on external testing equipment, the chip generates test patterns and analyzes responses internally. This approach is particularly useful for large and complex integrated circuits where external testing can be expensive and time consuming. Next we see about the BIST architecture and application. A BIST circuit consists of three main blocks. The test pattern generator creates input patterns automatically. The circuit under test processes these patterns. The output response analyzer checks the output and generates a compact signature. BAST is widely used in microprocessors, memory circuits, communication devices, embedded systems, and system on chip applications because it reduces testing cost and improves reliability. Hope you all understood the concepts. Thank you.